A black hole the mass of Earth could be smaller than a marble. Yet from hundreds of light years away, it might look, at first glance, like just another planet passing in front of its star. Astronomers are now seriously asking, have we already seen tiny black holes and filed them away as weird exoplanets? To see why this confusion is even possible, we need to talk about how we detect most exoplanets. We almost never see the planets directly. Instead, we watch stars and measure their brightness with absurd precision. When a planet crosses or transits in front of its star, it blocks a tiny fraction of the light. The star briefly dims, then brightens again. From the depth, shape, and timing of that dip, we infer the planet's size, orbit, and sometimes even hints of its atmosphere. It's like inferring the shape of a moth from the flicker it casts on a street lamp without ever seeing the moth itself. Here's the key. The transit method assumes that whatever passes in front of the star is opaque and roughly disc-shaped. A gas giant, a rocky super-Earth, even a puffy hot Jupiter all behave this way. But gravity doesn't care about our assumptions. A compact object like a black hole doesn't just block light, it bends it. According to general relativity, mass curves space-time, and light follows those curves. So a tiny black hole drifting in front of a star would act like a gravitational lens, warping and magnifying the star's light rather than simply casting a shadow. The result is a light curve that can look almost planetary, but with some very strange twists. Imagine watching a star and seeing it brighten slightly before it dims, then brighten again as the object moves away. That initial brightening is the telltale sign of gravitational lensing. As the black hole approaches the line of sight, it focuses more of the star's light toward us, like a very weak, moving magnifying glass. Only when the black hole's tiny event horizon actually overlaps the star's disk does it block any light at all. And because the black hole is so small, that blocking can be negligible. To a pipeline designed to find neat, U-shaped dips from planets, this combination of magnification and subtle dimming can look like noise, or like an impossible planet with contradictory properties. This is where things get really weird. Some transit surveys, like NASA's Kepler and TESS missions, have found candidates that don't quite fit the usual categories. Their inferred sizes and masses don't line up with known types of planets. For example, an object might appear to have a very small radius from the transit depth, but its gravitational tug on the star, measured by radial velocity, the tiny wobble in the star's spectrum, suggests an enormous mass. That combination would imply a density far beyond any known material, much higher than even a neutron star's crust. Instead of a super-dense exotic planet, a more natural explanation is a compact object, a white dwarf, a neutron star, or, in the most extreme case, a black hole. Recently, theorists have proposed that some of the odd signals in microlensing and transit data could be primordial black holes formed not from dying stars, but from extreme density fluctuations in the first fractions of a second after the Big Bang. Unlike stellar black holes, which typically weigh several times the mass of the Sun, primordial black holes could span a huge mass range from asteroid mass up to thousands of solar masses. The especially intriguing ones for exoplanet hunters are in the planet mass range, say, from the mass of the Moon up to a few Jupiters. These would be utterly dark, no accretion disk, no X-ray glow, just pure gravity. If one drifts in front of a star, the only clue is the way it distorts the starlight. So how do we tell a tiny black hole from a weird planet, using only starlight curves? One clue is symmetry. A normal planetary transit produces a mostly flat-bottomed dip. The star dims to a certain level while the planet is fully in front, then returns to normal. A gravitational lensing event, by contrast, tends to produce a more peaked symmetric brightening, with the maximum magnification at closest alignment. A hybrid event, where a small black hole both lenses and slightly occults the star, can create a very distinctive W or bump plus dip shape. Another clue is color. Lensing is achromatic. It bends all wavelengths equally, so the magnification is the same in red and blue light. Planetary atmospheres, however, can absorb more strongly at specific wavelengths, slightly changing the transit depth with color. By comparing light curves in multiple bands, we can test whether we're seeing gas, rock, or pure space-time curvature. The challenge is that our current surveys were mostly designed to find ordinary planets, not to systematically hunt for planet-mass black holes. Their detection pipelines often throw away messy or single-episode events as artifacts. But as data archives grow, Kepler alone monitored over 150,000 stars for years. Astronomers are remining these records with new algorithms tuned to lensing signatures. They're also combining transit-style photometry with microlensing surveys like OGLE and MOA, which already watch for temporary brightening caused by compact objects in our galaxy. If even a small fraction of the unexplained events turn out to be primordial black holes, it would not only rewrite our catalogues of exoplanets, it could also reveal a hidden component of dark matter.